Hi everyone, my name is Amorita with student number 2024-32051. So today I will demonstrate about implementation neural network and Q-learning. So let's get started. Okay, we begin with cell 1 in the first section, and in this cell we import all the necessary libraries required for this practical work, and this include pandas and numpy for numerical and matrix data management, matplotlib and seaborn for data visualization and graphing, and a set of models from scikit-learn covering data splitting, feature standardization, and the core MLP classifier model and evaluation metrics. Okay, moving on the cell 2, command is used to load the clinical dataset name heart.csv into the data frame variable df, and the df head function is then executed to display the first 5 rows of the data as an initial representation result. And from the display output, we can identify various medical parameters of the patients, such as age, sex, CP, call, and the target column on the far right, and which acts as our dependent variable. Next, in cell 3, we execute the finfo function to analyze the structural characteristic of our data frame. And based on the output summary, it is confirmed that this dataset contains a total of rows or entries, and all columns contain numerical data types, either integer or floats, and no missing values are structurally detected at this stage. Next, in cell 4, we run the dfDescribe function to generate descriptive statistic for each numerical feature. And from this output table, we obtain the mean, standard deviation, minimum value, quartile values, and maximum value for each parameter. And for example, the average age of the patients in this dataset is approximately 54 years, and with a standard deviation of 9.08 years. Next, in cell 5, is the validation for missing data is further reinforced by executing df is null sum, and the output shows a value of 0 for all variables, and this successfully proves that our dataset is clean for any missing values, and meaning no data imputations is needed. Entering in cell 6, we check for data redundancy by counting the identical rows in this dataset using df duplicate sum, and the program output informs us that there is exactly one duplicate row in the dataset, which could potentially cause bias in our machine learning model if left untreated. Next, in cell 7, we removing duplicate data, and to handle the duplicate data found in the previous cell, we execute the df drop duplicates in cell 7, and this step removes the single duplicate row from the system memory, making our dataset completely unique. Next, in cell 8, we begin the exploratory data analysis stage by visualizing the distribution of the target variable using a count plot. And the bar chart shows the ratio of healthy patients represented by level 0 compared to patients diagnosed with heart disease represented by level 1. And the proportion between both classes is well balanced, and indicating that the dataset is ready for training without risk and imbalanced dataset problem. Next, in cell 9, the analysis continues by examining the correlation of the sex variable against the patient's health status using the hue target argument. And the result of this cell, the multicolor bar chart, presents a comparison of health status distributions between male and female groups, and providing an initial clue regarding the diagnosis patterns based on gender. Next, in cell 10, is about the visualization focus on the CP feature, and which standards for chest pain type representing for a distinct category. And based on the chart interpretation, patients with certain categories of the chest pain display a significantly higher frequency of positive heart disease diagnosis compared to other types. Next, in cell 11, we analyze the FBS variable or fasting blood sugar to evaluate whether a fasting blood sugar level above correlates with the heart conditions. And the result, this bar chart distribution, we can map the pattern of diabetic patients again their heart disease status. Moving on, cell 12. Visualization is performed on the risk-take variable, which stores electrocardiogram data recorded while the patient is at rest. And this chart groups the data into three subcategories of medical findings, revealing which category shows the highest trend and heart abnormality vulnerability. Okay, next in cell 30, we analyze the exam feature or exercise-induced angina and to see if chest pain stimulated by physical activity relates to the target. And the output visualization provides a clear contrast showing a noticeable difference in health status proportionals between patients who experience angina during exercise and those who do not. Okay, in cell 40, a mapping is created for the slope feature, which represents the slope of the ST segment during peak physical exercise. And the output of this cell shows that the specific slope pattern on the heart curve strongly correlates with an increased change of the heart in disease occurrence. Next, in cell 50, the artificial network architecture is initialized via the MLP classifier command and trained using the train data with the fit function. And after the model finish, learning the data patterns, predictions are made on the test set, which are then project into a confusion matrix. Next, in cell 60 and cell 70 is the process advanced to data pre-processing before modeling, and the predictor features are isolated into matrix X, and the target column is placed into vector Y. And next, using the train test split function, the data is randomly divided with a proportion of 80% for the training set and 20% for the testing set. And this is followed by the application of a standard scalar object to uniform the range of numerical values, which stabilize the weak convergence optimization in our neural network algorithm. Next, in cell 18, the artificial network architecture is initialized via the MLP classifier command and trained using the train data with the fit function. And after the model finish, learning the data patterns, predictions are made on the test set, which are then project into a confusion matrix. Confusion matrix on the screen documents the real distribution of the model's prediction, breaking down the counts of for true positive, true negatives, false positive, and false negatives. And then the last cell is about final classification report. In this cell classification report function to comprehensively measure model performance, and if we see the result of the cell according of the normal evaluation table on the screen, our neural network model achieved a precision score of 0.78 for healthy class and 0.86 for the heart disease class, and the recall values reach 0.86 and 0.78 respectively. And overall, the model records a global accuracy of score of 0.82 or 82% out the 61 test samples. And this outcome proves that our basic multilayer perceptions architecture performs effectively in classifying heart disease risk data. And then, so we moving on the second part of this lab report, the focus shift to the implementation of key learning algorithm. So we begin with the cell 1, and here we import the NumPy and Matplotlib libraries. Next, we define the environment parameter for S4 grid word agent, and resulting in a total of 60 states on 4 possible actions or movement directions, and the goal position is set at index 50. And finally, we analyze a queue table of size 60x4 and file with zeros to act as the initial memory matrix for our agent. Next, in cell 2, we define several vital hyperparameters that control the learning process of the agent. And this parameter include learning rate of 0.8 to regulate the adaptation speed of new values, discount factor of 0.85 to determine the weight of future rewards, and an exploration probability or epsilon of 0.2 to balance exploration and exploitation. And this stimulation process is configured to run for 100 epochs for training episodes. And next, proceeding to cell 3, we define a transition function named getNextState, and this function maps the movement of the agent within the row and column coordinates of the 4 x4 grid matrix based on the execute action index 0 for up, 1 for down, 2 for left, and 3 for right. And inside this function, boundary logic is implemented so that if the agent attempts to move past the grid walls, it remains in the current state. Moving to cell 4, we execute the core code block that runs the agent training cycle for 100 episodes using the Bellman optimality equation. And each episode, the agent begins its movement from the initial starting point at index 0, utilizing the epsilon greedy strategy, and the agent switches between exploring new random actions or exploiting the best known action from the current queue table. And every time the agent transitions to a new state, the numerical value in the queue table is updated and iteratively until the agent successfully reaches the design goal state at index 50. And finally, in cell 5, we visualize the results of the agent learning process. The code takes the maximum estimation value from the queue table for each state and reshapes its dimension back into a 4x4 matrix and plots is using cool-warm color map. And for the result of cell 5, looking at the graphical output on the screen, we can analyze the distribution of key values learned by the agent, and the grid cells show the clear increase in color intensity and numerical values as they get closer to the goal position at the bottom right corner. And this conferring pattern scientifically proves that our agent has successfully discovered the optimal path policy to reach its final target. And to conclude the series program demonstrations, we have successfully implemented two district artificial intelligence approach. And first, the multi-layer perceptions neural network, which provided an 82 accuracy score in medical classification, and second, the Q-learning algorithm, which successfully trained an autonomous agent to master spatial navigation within a grid world environment. And that completes the entire presentation of my practical report. Thank you very much for watching, and see you in the next video. To summarize the entire exploratory data analysis phase in cell 50, we construct a correlation matrix using heat map with decimal annotations, and if we see the result of cell 50, this cool warm color map quantifies the strength of a relationship among all variables in the dataset, and coefficients closer to positive 1 or negative 1% a strong correlation, establishing which medical features we highly important for our model to learn.